Hello everyone. This is the video lecture of section 8.5, first part of Calculus 2, Math 2520. Okay, so this is the lecture for the class on Monday, April 6th. And then we'll cover the first half of section 8.5, which is very, very important section, power series. And then we will cover second part of section 8.5 on Thursday, April 9th. So we'll cover just one section over a whole week because it is that important. What you have done so far in section 8.1 through 8.4, various of theories about convergence of sequence and series, various of tests about convergence or divergence, is all geared for this power series. Okay, so then what is power series? A power series is a series of this form. That is C0, C1x, C2x squared, and so forth. Where x is a variable, so you can change the values of x because x is a variable. And CI's are called coefficients, obviously. Coefficients. Okay? So, power series is a function of x because given values, different values of x will potentially give you different output. Now, of course, infinite series may not converge, right? Depending on x values. For sure, when x equals 0, it'll be C0. Yeah, that is conversion. For different x values, you never know. Depending on the behaviors of CI, if coefficients growing so fast, it may not converge for many values of x. On the other hand, if C1, C2, C sequence of coefficients, Cn, goes to 0 so fast, then even for large values of x, it might be convergent. Anyway, power series is actually a function. It is a function of x whose domain is the set of the value of x for which this power series, I'm going to call it 1, the series converges. As you can notice that I'm not going to write down every single word from lecture notes because you have a lecture note, okay, in the course web page. As I said always, you have to get a copy, print out of the lecture notes I uploaded in the course web page, and then you want to, write your own comments on it. Okay, while we go through this. So, power series is some strange way of describing a function of x, all right? Using infinite series of this form. And another view of power series is, it looks like a polynomial, in a sense, because it involves only positive, non-negative integer power of x. You don't have square root of x. You don't have actually 3 over 2. Only integer power of x. The differences between polynomial and power series is this can go on and on forever. So-called degree would be infinity, right? Degree of a polynomial was the largest power of x among the non-zero terms, right? Here, there's no end, right? Unless coefficients stop being 0 forever. So polynomial is a special case of power series when your coefficient Cn becomes 0 at certain point and on, right? So kind of like polynomial of infinite degree. Okay? Anyway, power series is a function of x, whose domain is the set of only values of x for which this is convergent, so that you have an output defined. So let's consider the most basic. If Cn equals 0 for all m, what do you get? Your power series becomes this. X to the n, right? If all coefficients are all constant 1, that would be what kind of series of this? You keep multiplying by x to get the next term. That's precisely a geometric series, right? With common ratio. So, we know that this is 1 over 1 minus 6. If absolute value of x is less than 1. Or undefined otherwise. Okay? So this simplest power series is same as 1 over 1 minus 6, value-wise, for all x between -1 and 1. Okay, this is probably the simplest power series. Now, this is a power series centered at 0. We can expand this thing not just around 0. We can think about this power series. Cn. Okay, instead of x, we have x minus atn. So that would be C0. Keep going, right? This is power series about a power series in x minus a, or you can say power series centered at a, or you can say power series about a. Okay. This is a power series when a equals 0, right? All right. Now, in power series, we use this notation. As usual, 0 factorial is supposed to be 1. And something to the 0 power is 1, as you know, for all x. Now, we already knew this. What we didn't know, what we didn't use is that we excluded the case 0 to the 0th power, all right? Even for alpha equals 0. Okay? So, from now on, so this is the case when you, in this notation, if you put x equals a and n equals 0, n equals 0 will give you what? N equals 0 is C0 and x equals a. When x equals a, C0, 0 to the 0th power. Normally, 0 to the 0th power is not defined. So strictly speaking, this notation is not going to work for x equals a, n equals 0, right? But what we wanted was C0. That means we want 0 to the 0 power to be 1 for convenience of notation, all right? That's why we accept this. Anything to the 0th power, even including 0 to the 0th power, is defined to be 1. Okay? It's not causing any contradiction or trouble. Okay? This is just convenient. Okay? So anyway, so both 1 and 2. I think we want to call it 2. Yeah. 1, 2. So when x equals a, therefore if x equals a, then, as I said here, x minus 18 will be just C0. All right? So power series at a, around centered at a, always convergent when x equals a. which is just constant times C0. Now, let's consider a power series which are not this special, but okay, more general case. Think about your two power series n factorial x to the nth a b x minus 2 C You know what? I'm going to change a little bit. Now, it was n, right? I'm going to cover a little bit. Okay. Let's cover this. X minus 2 to the nth over n 3 to the nth. Okay? Now, this is different from the lecture note. I want to cover a little bit more generals here. C x minus 1 to the nth over n factorial. Okay? Now A. We want to investigate the behavior of this power series. Okay? Investigate means that, first of all, I want to know for what kind of values of x this is meaningful. It gives you an output defined. Okay? Now, so we want to use some kind of convergence test. But then, all the materials from 8.1 to 8.4. There's one test which was very appropriate, very useful when you have exponential feature, something to the nth power. Right? What was the name of that test? Something very useful, efficient to capture that exponential feature. That was ratio test, right? So the main tool of analysis of power series is ratio test, because by definition, power series is supposed to have a feature of exponential function, a geometric series feature. All right. So we'll use ratio test. Now this is our so-called nth term of the series, an, right? This is our an. So we want to use ratio test whenever we deal with power series. So what is an plus 1? N plus 1 factorial x to the n plus 1. What is an? Well, n factorial. Now, n plus 1 factorial is 1, 2, 3, keep multiplying all the way to n and n plus 1. Divided by n factorial is 1 through n. Then 1 through n, 1 through n cancel. Only n plus 1 is remaining. This all cancel except for, so you have this one. So, what was the ratio test statement? If the limit of ratio of consecutive terms, if the limit of that is less than 1, then absolutely convergent. Greater than 1, then it is divergent, right? Exactly 1, inconclusive. It can be convergent or divergent, it can be anything. This one is, now look at this. N grows to infinity, absolute value of x some fixed value as n goes to infinity. If x equals 0, then the whole thing is 0, so limit is 0. So convergent, right? But if x equals 0, if x is anything other than 0, non-zero value times n plus 1 is going to infinity, right? So it's convergent, this is divergent. So this series convergent only when x equals 0. Everything else diverges. Useless, basically. Okay. This works only for x equals 0. Why? Because your coefficient Cn is an vector, it grows so fast, no matter how small x is, unless it is 0. Well, 0.1 to the nth power going to 0 fast, but not enough to cancel in factorial growth. That's why it goes in divergence. So the series, the power series, converges only for 0. Now, let's do C first, okay? Because C is easier. Let's do C first, this one. Again, this is your AN. AN plus 1 over AN is x minus 1 to the nth plus 1 over n plus 1 factorial. Now, divided by AN is multiplied by reciprocal of AN. Multiplied by reciprocal. So you will have this. Again, all cancel but 1. All cancel except for this. So you have this absolute value x over n plus 1. So if you take the limit of this sequence, what do you get? Give me x value 10. 10 over n plus 1 as n goes to 0. As n goes to infinity. Going to infinity, right? What about million? Million over n plus 1. So million is fixed. N goes to infinity, still going to 0. It turns out that it's going to 0 for any value of x. Once you fix the value of x, as n goes to infinity, it goes to 0. So less than 1. The limit of ratio sequence is less than 1 for all x. Therefore, the power series converges for all real number for x. Okay? So now let's consider B, the hardest one. Okay. Let me check the recording. Okay. The last one, B, is. Okay, so this is our AN this time. Again, we will use ratio test. AN plus 1 over AN. N plus 1. X minus 2. N plus 1 over N plus 1 times 3 to the N plus 1. Right? Replace N, every N with N plus 1. Divided by AN means multiplied by its reciprocal. So, N 3 to the N over N. So we have to take epsilon here. Now, again, this is slightly different, slightly more complicated than the example on your lecture notes I uploaded. You have a 3 to the N presence here. Now this one, it cancels except for everything except for 1. So you have 1 over n plus 1, no, n over n plus 1, and then absolute value of x minus 2 over 3. Right? 1, 3 is remaining. So, if you take n goes to infinity, n over n plus 1, 3. So, what happens? The limit is, this one is going to go 1, right? So, limit of the ratio sequence is absolute value of x minus 2 over 3. Okay? This is the limit. So what? What was the ratio test? When the limit of the ratio sequence of immediate terms less than 1. If that is less than 1, you get absolute convergence, right? If it is less than 1, absolute convergence, right? Absolute convergence. If it is greater than 1, divergence. Now, what is this? That is so if okay, the power series, that means the power series converges absolutely if this one is less than 1, which means this one is less than 3. So IB minus 3. So you can say that minus 1, 2, 5. So when you have around 2 plus 3, so 5 minus 3, negative 1, right? Around 2 plus minus. From here to here, all values of x here, your series will be convergent, absolutely convergent. I'm going to copy this one because I will probably erase this x minus 2 to the nth over. Okay. Now, however, the series diverges if this one is greater than that limit. This limit value greater than 1, which means greater than 3. So it is, x is less than negative 1 or x is greater than 5. Then you will have a divergence. Okay? But we don't know. So this one is convergent. This one is divergent. Divergent. All right? Divergent. Here. But we don't know about exactly endpoints, negative 1 and what about exactly negative 1 and 5? That's when the limit of ratio sequence is 1. That's the blind spot of ratio test. Remember? When the limit of ratio sequence is exactly 1, the series still could be convergent or could be divergent. You never know, right? So, let's consider case. So, the first case, convergent case, divergent. What about x equals negative 1? Then what happens when x equals exactly left and value? Then the series will be what? Negative 1, negative 2, so negative 3 to the nth power over n, 3n power. Right? That will be the value of the power series. Now, if you combine it, a to the nth over b to the nth is, what is it? A over b to the nth. Minus 3 over 3 entire to the nth. That is exactly negative 1 to the nth. What kind of series is this? It should be starting from 1. Sorry about that. 1. Okay? Otherwise, this wouldn't be conversion. 1 starting from 1. So it is minus 1 plus 1/2 minus 1/3. It's almost alternating harmonic series, except that you start with negative 1 rather than positive 1. So negative up, alternating harmonic series. But anyway, this is alternating series whose absolute value of an 1 over n goes to 0 and decreasing. By alternating series test, this is conversion. By alternating series test. Right? Finally, the right endpoint. What about x equals 5? And you get 3 to the nth, right? 3 to the nth over n tenths. That is exactly harmonic series, isn't it? Harmonic series. We know that this is divergent. All right? So, the set of all convergent, so that means the series convergent if and only if x is on this interval, including -1 but not including 5. So the set of all values of x, for which your power series conversion will be this interval. You know, from this center point, plus minus 3, right? For this one, 0. For this one, only at 0, at one point. This one converges everywhere, right? Minus infinity to infinity. This one is just 0 only, right? Just 0 only, 1 point set. This is negative infinity to infinity, all right? And these 3 examples actually exemplify 3 different cases. It turns out that every power series will be fall into one of these 3 cases. Okay? That's the theorem 1. Before I go forward, I want to make a comment on this. First of all, if you had n squared, then you will have n squared, right? And what do you get? You get convergence also at the right endpoint, right? 1 over n squared will be convergence. Then your series will be convergence also at the right endpoints. However, this value 3, so-called radius of convergence, doesn't change. This value does not change, right? This things does not change. Okay? If you have n over here, then you will have n over here. So even this one is divergent, right? Not to mention this one, right? In that case, it'll be -1, 5. None of the endpoints will be included, right? So, this n or 1 over n makes a difference only at the endpoints, right? Whether minus x equals -1 will give you convergence or not. However, this value 3 does not change. Because when you do that, this one will not change. Even if you have an n, then you have to switch this order, right? Switch this order. Still, that's going to go to 0. When you have a square, still, this one goes to 1, right? So whether you have an n on the top, or n in the bottom, or n square, this value of the linear ratio sequence does not change. So the size of the interval on which your power series is convergent does not change. However, you can change the convergence of the endpoints. All right? That's very, very interesting property. Okay? Another thing is that, what if I have not in 3, but 5? Then you will have 5, 5, 5, 5, 5. Right? So instead of 3, you will have 5. So it's going to be 7 and probably -3. The size of the interval will change if you have different exponential functions, right? Competing exponential function can adjust size of the interval on which your power series converges, right? So you can have many different sizes of interval. We call it interval of convergence. Okay? So anyway, so let me just give you a summary of these things as a theorem. It turns out that these 3 examples covers everything, every power series. That is theorem 1. For any power series, okay, x minus a to the n, there are only 3 possibilities. First, the series converges only for x equals a. Example 2a. Okay? Example 2a, for example. Second, the series converges for all x. Okay? For all x in the real number, like example 2c. Third case is this one. There exists, you know this symbol, E flipped means there exists. There exists. There exists. There exists a positive real number R such that the series converges absolutely such that the series converges absolutely for x, which is satisfied is within R, but the series diverges for the x value greater than R. Okay? So you have that kind of number R. Okay? then we call that R is radius of convergence. R is called radius of convergence because this one covers from A, R, A plus R, distance of R, A minus R. Okay? Inside you have a convergence, guarantee of convergence. Outside, divergence. Exactly at the endpoints, you never know. It's a case by case. Sometimes convergent, sometimes divergent. It depends on the case. All right. So this is the general case. So I told you this is radius convergence, and in that case, for convenience, we define this case as radius of convergence 0. In this case, radius convergence infinity. All right. Now, definition of interval of convergence. So, you have three possibilities. Your set of all the x real numbers for which your series is convergent. For A, you have only 1 point, right? Only at 1 point you have convergence. Here, whole real line, you are convergent. In this case, you have 4 possibilities. Okay? That is, you could be convergent only inside. Or you could be convergent at the left endpoint, but not the right endpoint. Just like the original case B, right? Or it is possible that you can have convergence only at the right endpoint, but not at the left endpoint. Or you can have convergence at both endpoints. That's when you have a n squaring down here. Original one was this, right? And 3 to the n. All right. So these are called interval of convergence. Okay. So interval of convergence. Because interval of convergence is set of all real numbers of x for which the given power series converges. But according to this theorem, that set of all values of x for which power series converges will be either 1 point set or the whole line, or look at this interval, isn't it? You can't have, bunch of several intervals combined. You can have convergence here, convergence, but not in between. You can't have those cases. You will have a single interval. It could be a collapse to a point. It could be the entire real line, but still a single interval. So we call it interval of convergence. So for the case 3, you have 4 possibilities interval convergence. Size is same, R. Radius convergence is same. Within the same radius convergence, you can have those 4 different cases. All right? So this example is most helpful to go over because these are relatively easy ones. This requires the most work to analyze. Especially you have to check the convergence and divergence of endpoints. Okay? So this concludes the first part of section 8.5. Okay? This is a lecture for the class on Monday, April 6, 2020. Okay? I'll see you next time.